Hello and welcome to the Capstone torque vectoring of the winter spring sequence. To start, torque vectoring is a technology implemented in modern to future cars today. Its purpose is to control the power applied to each wheel through a software algorithm rather than using mechanical parts, ultimately helping a car's driving dynamics by controlling wheel slippage and yaw rate. Our team lead was me, Ben, and our sponsor was Hector Amazola, president of Viking Motorsports. And our team members were Isaak, Amir, Grant, Matthew, Austin, Simon, and Drew. Now, we'll be starting with a little demo of our Python simulation. What you're looking at here is a car accelerating with the left wheel at 100% and the right wheel throttle at 0%. And the last parameter is the steering angle, which is set to 100 degrees and is turning the car to the right. And to explain yaw rate really quickly, it is the rate at which an object will rotate. So notice in the graph here that the yaw rate of the car and desired yaw rate of the car is off by a bit. What we want to do is be able to overlap these two variables by changing the ratio of power. And going on to the next slide here, by inverting the power applied to each wheel, we almost overlap the yaw rate and desired yaw rate. And this is exactly what we're looking for, is we want to have yaw rate and desired yaw rate to be as close as possible. Now it's just a matter of creating a lookup table that our microcontroller can use in the car, and our next slide will explain that.
Here we have a live demo of a miniaturized version of our lookup table generation. This lookup table takes in the velocity and steering angle in order to find the requested throttle percentage to push to each wheel. In order to speed up the process of the calculations, we use multi-threading, which is visually represented here by the circles. Each circle is a calculation that's currently being worked on, and once the calculation finishes, the index in the array gets shifted to an X. Now, we'll pass it on to the project overview.
In our overview of the project, we aim to give Viking Motorsports tools and code for a microcontroller to replicate torque vectoring for future members of the organization. As I mentioned earlier, torque vectoring is a process of splitting power between two wheels, the rear wheels in our case, to hopefully solve the problem of mismatched results of yaw rate and desired yaw rate. If this is successfully implemented, it would help the Viking Motorsports car's characteristics by preventing it from spinning out under hard turning and acceleration. In the car industry, this is also becoming a prevalent feature in electric cars that would provide better traction and ease of manufacturability. Some of our main features here is the Python simulation, which its main use is going to be using the Magic Formula Tire model, and the Simulink simulation, which its main use is going to use the Burkhardt tire model. And then we have the microcontroller code that results from that, and we have continuous integration and source control.
So the first main features of our project is the Python simulation. This simulation was very important and helped us understand how the torque vectoring system could work before we built it. We use models and formulas about how torque vectoring works from published studies. By adjusting these formulas, we made our predictions more precise. The Python simulation is the core of our project, and it can also be used in the future for more improvements and testing. So let's look at the results from our Python simulation. This graph shows how the car and wheel velocity relate to wheel spillage over time. As you can see, our system lowers wheel spillage as the velocity goes up. This is really important because it helps the car stay controlled and stable when driving fast. These calculations are key to our project because they show us how the torque vectoring system is likely to behave in real-life situations. Our system is designed to lessen spillage, especially at the higher speeds. So the second graph is shows how the yaw rate and the desired yaw rate change over time. The closer these two values are, the better our system is performing. As shown in the graph, our system effectively managed to keep the actual yaw rate very close to the desired yaw rate. Which means our torque vectoring system is performing as planned to improve the car control and movement.
Thank you, Amir. Just like the Python simulations, the Simulink simulation consists of torque vectoring formulas and vehicle dynamic models, such as the slip ratio calculations shown here. The simulations output to a graph to visualize our desired yaw rate compared to our actual yaw rate. And although they're functional, this is a fundamental simulation that can be built upon for future improvements in testing. And then here we have two graphs displaying our simulated yaw rates in Simulink over roughly a 30-second time period. The graph on the left was run with a steering angle of 100 degrees turning right and a torque of 40 and 60 at the left and right rear wheels respectively. The graph on the right shows the same steering angle, but instead using a 30-60 split of torque. And looking at these two graphs, we can see that the actual yaw rate isn't far off from the desired. And with more fine tuning, we can close the gap on the actual and desired yaw rates. And I'll now pass it off to Grant to talk about microcontrollers.
Another important aspect of our project was the microcontroller code. The microcontroller code is the code that would actually be running in real time on the car during competitions or whenever it's being driven. It consists of several major parts, including the pedal controller, frequency measurement, SD card logging, communications, torque vectoring calculations, and the lookup table. To go into detail on a few of these, the communications are everything having to do with the microcontroller taking in information from off the microcontroller and outputting information onto somewhere else. We have 5 different protocols that we're using in the microcontroller code. The analog to digital controller, or ADC, the digital to analog controller, or DAC, CAN, which interfaces with another Capstone, SPI being used for SD card logging, and timers used for encoding frequencies from the wheels. We'll have more on that later, but another main component is the torque vectoring calculations, which uses the lookup table that's generated from the Python simulation, taking in velocity and steering angle as inputs and outputting a ratio between the left and right throttle. Lookup table does interpolation by default. We have linear interpolation between entries in the lookup table, and the output is scaled afterwards by the throttle input from the car. And I'll pass this off to Simon.
The frequency measurement feature is designed to accurately measure the velocity of the car using the frequency of wheels. There might be some outliers due to inconsistencies with the microcontroller sensor. So we have a function that filters out the outlier to provide a more accurate speed measurement. It uses a 10% threshold to identify those outliers. And if the difference between the current frequency and the previous frequency exceeds that threshold, it is considered an outlier. And when that outlier is detected, the algorithm uses the previous frequency value to recover from that outlier state. And now I'll pass off to Matthew.
Our torque vectoring system is fully open source. So for source control, we're hosting on GitHub and we're storing it under the Viking Motorsports GitHub organization. We're also doing our continuous integration through GitHub, and we're using GitHub Actions for that, which allows for seamless integration into the repo. The project is licensed under the BSD3 clause. It's the same as many of the STM32 libraries we're using. It's a fairly popular license in open source, and the terms and conditions are very similar to the MIT license.
I'll be talking to you about some future features that we might consider. Some features that we would have liked to have implemented is rigorous testing of the microcontroller code. Unfortunately, it is rather hard to do since it is dependent on Viking Motorsports to have a running car, and it wasn't possible at the time. And then having a cross-examination of our simulations to dictate what simulation is more accurate would be a good project on its own, but due to our time constraints, we didn't have time to do that. A future team using four-wheel drive for torque vectoring would be also a very large project on its own, as it has to take into account the physics of the front wheels, and a rework of the simulations would be required for that. And a closed loop feedback system that changes the torque ratio based on various sensors would be an ideal system, but Viking Motorsports did not have the resources to achieve that either.
So for our PID controller aspect of the project, we wanted a simulation that was focused on the PID aspects of the simulation. And this would allow us to simulate very specific characteristics, including things like yaw rate and desired yaw rate, but also things like vehicle velocity, wheel velocity, horizontal velocity, and slippage. And so we developed a simulation that we're working on in Rust, which gives us various performance benefits over a Python simulation. For the graphical aspect, we're using Plotters RS, which allows us to plot static graphs of the simulation data and view them. And then we can also export that data into a CSV file for viewing into other applications such as Excel, so we can do more with that data. And much like discussed earlier in the Python simulation, this also will do lookup table generation, which can be used on the microcontroller side. And this component of the project is still being developed, and so development on this is ongoing.
The architecture of the project, we've mostly focused on the microcontroller code. We've created this diagram, which is color-coded to indicate different parts of the microcontroller accessing information. The blue-colored parts are representing actual communication with pins on the microcontroller, and the red parts are anything that is off the microcontroller board. For example, we have the CAN Capstone information coming from another microcontroller or otherwise outside of the one that's running the torque vectoring code. Everything else is happening within the microcontroller, and we're focusing on this main loop of computing the torque vectoring that will be written out to the DAC and eventually sent to the wheels.
Here, we convert our analog inputs into digital data using an analog to digital converter, parsing out throttle input and steering wheel angle. We add in the velocity, which has been pre-checked for outliers from timers. And with these three data streams, we are then able to calculate the power ratio, which then gets converted back from digital to analog, where the power is then pushed to the wheels. We have also set up frameworks for more calculations by allowing data to flow from the CAN bus into the microcontroller, which can then be used for future calculations. We also set up the framework for SD logging through the SPI communication channel, which allows users to log any data they want through the SD interface.
At the start of our project, we split our team into 4 main groups to work better. These were the Python simulation group with Amir, Ben, and Grant, the Simulink group with Austin and Joe, the microcontroller group with Ben, Grant, Isaak, and Saimon, and also the unit testing and integration with Matthew. This way we could work on different things at the same time and making us faster and more efficient. We also work together a lot, helping each other learn and feel like part of a team. Everyone also collaborated and helped with documentation and presentations. Before diving into the implementation, we researched existing techniques and strategies related to torque vectoring. We got a very helpful research paper by João Pedro. It provided models and formulas that we then utilized for our Python simulation, Simulink, and also the microcontroller code.
Thank you, Amir. Our timeline was pretty straightforward. We chose the project on January 30th, and from there we had several weeks to divide into teams, the teams that Amir previously discussed. And then we started our research while also completing our project document, which outlined our plans and goals for the project. That project document was due March 21st, and we presented it the following day. By May 29th, the simulations and Microcontroller code were finished, and then the project will be delivered to the sponsor on the 12th of this month. As Amir mentioned, we used a research paper for a lot of our models and calculations. This picture here shows a Simulink model that we use to replicate in Simulink for our own simulations. The model takes in the steering angle and the torque from both the rear wheels to output various calculations, such as the slip ratio, which I showed previously, the rolling force, vertical loads, and etc. And then each block was built one at a time, and once all completed, connected together for a final product. And from there, we were able to run simulations and begin testing. On that topic, I'll go ahead and pass it off to Matt for unit testing.
Yeah, and so for this component, we also incorporated unit tests and continuous integration to improve our code's reliability of the simulation. So for the Python simulation unit testing framework, we're using PyTest, and this allows us to perform validation on the various components and calculations used in the simulation. And then these PyTests are also run by our continuous integration system automatically. And so that automatically installs the necessary dependencies through pip and then runs them. And currently for the linting and unit testing process, it runs in about 30 seconds.
And then as Matt mentioned before, we did use the BSD3 clause licensed on our GitHub code for future collaboration. This BSD clause provides commercial and private use, modification, and distribution, and then liability and warranty limitations. And then we will be successfully delivering the final product to Viking Motorsport.
Some of the unexpected events that we kind of came across when creating microcontroller code is that the SD card logging became a lot more sophisticated than expected. We had to use a library that is used for writing out to a file rather than strictly sending data by using the SPI communication protocol. We found out that SDIO was interfering with other parts of the microcontroller by debugging it, by printing out data, but alas, SDIO was preventing input and output. So ultimately, we moved to the SPI communication protocol instead, as it used fewer pins, and it didn't interfere with other communications. Our lookup table format changed since we wanted to figure out if throttle should be a direct input into the lookup table, or rather a scalar after the output has been found. And lastly, our general work requirements were a little higher than we initially expected due to the number of concepts that people had to learn in order to write code, and being able to interpret results as the correct calculation took time from us as well.
So we shared our project with our sponsor from Viking Motorsports, Hector Amasola. He gave us some feedback, some positive, mostly positive, but also some constructive criticism or negative feedback. He spoke on the fact that the simulations worked and they output graphs for viewing desired yaw rate and actual yaw rate and different torques and steering angles. Basically, the simulations did their job, and the 2D lookup table similarly was able to be generated and able to help determine the ratio of applied torque to each wheel. This project will aid in the application of these systems for Viking Motorsports' current and future use and their electric vehicles. And the Hector acknowledged that the processes and relationships utilized leading up the simulations are clear and coherent. Hector did have some negative feedback, which was mostly about the inconsistencies with the Python and Simulink models. He specifically noted that we used two different tire models. We used the Magic model and the Burkhardt model, which would have been beneficial to stick to one model. Hector advised that we make those changes. And here's a quote by Hector. "The torque vectoring capstone fulfills the process for applying torque vectoring to Viking Motorsports' third generation electric vehicle." Thank you, and I'll pass it back to Ben.
Some of the lessons that we learned is, like I said before, in our unexpected events, it took us more time than expected to learn concepts. And so taking more time, especially in the initial part of the capstone, would have been a lot more beneficial. And delegating our tasks in a format of having different files for different members helped reduce our merge conflicts, and has helped us focus on what mattered most instead of spending time resolving conflicts. And our documentation of code on our microcontroller was rather lackluster, resulting in some confusion every once in a while. But ultimately, it was just hindering our group work efficiency in understanding each other's code. Lastly, we want to say thank you to all of our contributors, from our sponsor to the people from the electrical engineering Capstone. Thank you to Viking Motorsports that have made this project possible in their drivetrain design of the new 2023 car. Thank you to all the members who have diligently put in the work. And lastly, we hope that this project will provide future resources to students and further innovation in the world of car development. Thank you.